Hi, welcome back. In this video we're going to define capacitance, which is an important circuit property or device. And we're going to work through a couple of examples of how we can compute capacitance. Let's have a look. So first of all, a capacitor is a circuit element whose job it is to store energy in an electric field. It stores energy in an electric field. It does this with two conducting surfaces that are usually parallel to one another. And we call these conducting surfaces plates. And the plates do not have to be flat. They can be curved as long as they're parallel. And we've actually looked at capacitors a few times in this course so far, but we did not call them capacitors at the time. Now we're going to call them capacitors. So the conducting surfaces that are parallel with one another, or the plates, have equal and opposite charge in a capacitor. So we'll usually denote that as plus and minus Q. The charge comes about from a voltage source connected across the plates, right? So you usually have like a battery, and the battery is connected to a couple plates. In our discussion about conductors, we calculated the voltage, the electric field, and so forth between the plates of a capacitor, okay, though we did not call it that. So let me draw your attention to my figures here. I have three separate capacitors. I have the rectangular version, where you have two literal plates, right, flat plates, and we've calculated the electric field inside those plates before. In the middle picture, I have another capacitor, and this would be the cylindrical version of the capacitor, where you have two hollow cylinders, metal plates, and we've calculated the electric field inside that material there. And then in the third picture, this would be the spherical capacitor, where we have two spherical shells, and we've calculated the electric field inside those shells. So I want to be very clear that these are three separate capacitors, not one capacitor. Three separate ones. I've just drawn them all right now in the interest of saving time. So with charge on the positive plate Q and voltage across the plates V, the capacitance is defined as C equals Q over V, and you should have seen this in physics. You should have seen this in circuit analysis. Again, the positive charge, or the charge on one plate, divided by the voltage, or the potential difference across the two plates, that's defined as the capacitance. Now that's where you stopped in circuit analysis and in physics. And in our course, we're going to look a little deeper. And the bottom of this thing, the voltage, is the integral of E dot dl. And I'm going to drop the negative sign here because the capacitance is positive, and Q, the numerator, can be positive or negative, right? So we're just going to drop the negative sign and speak in terms of absolute value. Now for the charge, I want you to recall that the charge on a conductor, or the electric field, is normal, okay, to the surface of a conductor, and the charge inside a conductor is zero. The electric field inside a conductor is zero. So remember that the electric flux density is normal, and that is epsilon times the electric field in the normal direction. And from Gauss's law in point form, that was rho s, the surface charge density then. And so we can write the total charge then by integrating the surface charge density, E dot ds, like this. All right, so we can find the capacitance then, it turns out, in a very similar way as finding resistance. We just did that. We can either assume Q and then find V with Gauss's law, and then the Q would drop out, or we assume V and then find Q with Laplace's equation, and then the V would drop out. So either way, the assumed quantity drops out like we saw with resistance. Okay, the voltage dropped out for resistance. So we're going to work a similar process as you'll see in these examples. So let me draw your attention to this rectangular parallel plate capacitor over here. Each plate has a magnitude Q, charge Q. So we're assuming Q here. The electric field we've calculated many times now inside those plates as being rho s, the surface charge density on one plate, divided by epsilon in the x direction. So why is it in the x direction? Well, I've set up the plates so that the electric field is in the positive x direction. So I've given, so you'll see that each plate is along the x axis, and I've given the positive plate I've given the plate that's at x equals 0 the positive charge, so that way the electric field points in the positive x direction. So if you are presented with such a problem and you're not given the figure, calculate the capacitance of two parallel plates, then you need to decide how you're going to orient the plates. Okay, so I like x and I like the positive direction, so I've oriented those plates like that. And I'm also saying that this is the x equals 1 plane, although we're going to call the separation distance d. Now, we can assume that the charge is uniformly distributed about the area. And unless you're told otherwise, you can make that assumption, uniformly charged. So that means that rho s is q over s over epsilon in the x direction, and then I can simplify that a bit by bringing the surface area down here like that. So that's the electric field, and that was for, remember, the separating distance is much less than the plate dimensions, i.e. we have infinite plates. We talked about that. Now we've got the electric field, we can get the voltage, right? The denominator here, we're going to take the path integral of E dot dl. So the electric field is in the x direction, as we talked about. The length, along the electric field, we're going to go from x equals 0 to x equals d, the separating distance of the two plates. So the electric field is q over epsilon s ax in the x direction, dotted with dl. So what is dl in this case? Well, we're going along the x direction. The electric field is that way, and so we talked about this way back when we covered vectors. This is dx in the x direction. So ax dotted with ax is 1, so this just gives me the integral from 0 to d of q epsilon s dx. That's a constant as far as x is concerned, so when I integrate that I just get x and I plug in the distance d, and so I get this as the voltage. So you see we assumed q, then we got the voltage. Now when we compute this ratio of q over v, q divided by v, the q's drop out, and we get the capacitance is just epsilon, that should be s, excuse me, epsilon s over d. So some texts use s as the surface area, some use capital A as the area. But that's the capacitance of this parallel plate capacitor. All right, now I'm going to erase this and just kind of summarize what it is that we just did. Okay, give you a step-by-step process. So step 1 is you got to set up an appropriate coordinate system. And we used rectangular form here because the plates are rectangular, but you also need to choose your origin and decide how you're going to orient the plates. 2, we gave the plates a charge of plus or minus q. So this is assuming q. Okay, from there we found E with Gauss's law. Now I didn't show you those details in this video because we've already done it. Or we could use Coulomb's law, by the way. You see, Gauss or Coulomb. You see, we've already done these things when we talked about electric fields and Gauss's law and Coulomb's law. We just didn't call them capacitors at the time. And so then with the electric field, then we can use that path integral and we can find the voltage. Step 4, then you just kind of compute Q over V, and then Q drops out. Right? This is what we just did with the first example. Now we're going to repeat this process, but with the coaxial cable. So this is the middle picture. Now in the middle picture, we're going to assume again that each cylinder, so there's an outer cylinder and an inner cylinder, has a charge Q. Right? And I guess step 1 would be to set up the coordinate system, but I've already drawn the figure. Okay, and you can guess that we're going to use cylindrical coordinates. All right, so then step 2 is to give each plate plus minus Q. So I'm just going to choose to give the outer plate, the outer cylinder, plus Q, and the inner cylinder minus Q, and then the electric field will point radially inward, right? And we're saying that the inner cylinder has a radius A and the outer cylinder has a radius B, and this thing has a length of capital L. Now from Gauss's law, we can write that we can draw, you know, a cylinder on the inside of this thing so that it encloses negative Q charge. We've done this already. This would be the closed surface integral over the Gaussian surface of E dot ds. Right? Well, and again, the electric field points radially, so this is E rho, and it's normal to the surface everywhere, and it's equal in magnitude to the surface everywhere. So the dot product is nice, the integral is nice, and we get this. I'm moving quickly through this part because I expect that you can already do this, because we have already done this. So the electric field then is this thing here in the rho direction. Now V is equal to negative. You can have the negatives or not, but we need the negative in this case to cancel. But remember that capacitance is a positive quantity. Okay, we've got the path integral of E dot dl. So when I plug in E, I can remove all of these constants other than the rho. The rho is not a constant. And I'm going from A to B. So that's why I'm using the negative sign here, because I'm going from A to B, which is against the electric field. So then I've got 1 over rho left out, right? D rho, because it's rho that's changing. Rho goes from A to B, right? And so when I compute that, then this is the natural log of B minus the natural log of A. Using a property of natural logs, that's the natural log of B over A. So this becomes Q over 2 pi epsilon times the length times natural log of B over A, like that. So now step 4, find the ratio of Q over V. So I take Q divided by what I just got, so the Q's drop out, and I get C equals 2 pi epsilon times the length divided by the natural log of B over A. You see? That's the same process that we did for the rectangular form, only in cylindrical coordinates. Now, in the beginning of this video, I said that we could either assume Q and find V using Gauss or Coulomb's law, or you could assume V and then you could calculate Q using Laplace equation. So now I'm going to do the reverse now. Now I'm going to assume V and find Q just to give you a second way of doing this. So I'm going to erase what I've done here, and we're going to look at the third picture. Alright, so we're going to try to find the capacitance of two spherical conducting shells with inner radius A and outer radius B. Alright, so I'm going to assume V now, not Q, as I did in the prior two examples. So I can just give, it doesn't matter, but I'll give the outer shell ground, and then the inner shell I'll give V 0 volts. Okay, so that's me assuming V. So I've got the boundaries now, and so I'm going to solve Laplace equation. Delta V equals 0. Del squared V equals 0, excuse me. So from spherical symmetry then, the voltage is only going to depend on the radius. So now I need to write the del squared operator, or the Laplacian operator, in terms of spherical coordinates with only the radius. So this is not bad, actually. This is 1 over r squared. The partials can become full derivatives because there's only one variable. And I've got that. Now, I can multiply by r squared, and that's still 0. Right? So I need to integrate once. I have the derivative of something, in parentheses, equals 0. So when I integrate once, that means that that something is a constant. Like that. I'll call that constant C1. And then I can divide by r squared. So I've got C1 r to the minus 2. I'll write it like that. Now, I've got the derivative of something is equal to C1 r to the minus 2. So when I integrate again, this becomes negative C1 r to the minus 1, or over r, and then another constant of integration. Call that constant 2. Right? Integration, single variable. That shouldn't be a big deal. All right, now we apply our boundary conditions. So the voltage at R equals A, right, we're saying is V 0 volts. So that would be, so I plug in R equals A. This is negative C1 over A plus C2. And then I plug in the radius B is 0 volts, we're saying. So I plug in B like that. So I need to solve those two equations for those two constants, and the best way I think to do that is to subtract the first equation minus the second equation. C2 drops out, and I can solve for C1, and I get C1 is V0 over 1 over B minus 1 over A. And then I put C1 in either one of these equations, and I get C2 is equal to V0 over 1 minus B over A. Now, again, we're solving Laplace's equation. The voltage is completely specified. Right, here's what we're saying the voltage was. So now I've got C1 and C2. So this is A over A minus B minus 1 over R times AB over A minus B. So I didn't like having fractions of fractions, and so I just got a common denominator. I'll let you work the algebra out on your own. Now, not a common denominator. I multiplied by some factors to get rid of the fractions. Okay, so now I've got the voltage. The electric field is the opposite of the gradient. And so in spherical coordinates and in one dimension, this is not bad. This is just minus dr v in the r direction, right? And I'm using full derivatives there instead of partials because there's only one variable. And so when I do that, so here's r. So this guy goes away. It's a constant as far as r is concerned. And so here I've got r to the minus 1. So when I differentiate that, I'll have an r to the minus 2. So I've got AB. The negative goes away because of the negative coming down in front, canceling. R squared B minus A, AR, like that. So there's the electric field. Now, let's get Q. Q, at the beginning of this video, we said was the surface integral of D, which is epsilon times E, dot ds for a conductor. And so we have epsilon. So what's changing now across our surface? Well, we've got rho as being constant. Rho is constant. And so we've got phi changing. Phi goes from 0 to 2 pi because it's an entire sphere. And theta changes from 0 to pi. So over the surface, we've got theta going from 0 to pi, phi going from 0 to 2 pi. Right, we're integrating over this entire contraption. AB V0 R squared B minus A. And do you remember what ds was in this case when phi and theta were changing? It was r squared sine theta d phi d theta. So I'm going to write that down. R squared sine theta d phi d theta. Like that. So I've done the dot product already because E is parallel to S. Alright, so I do this integration and the r squareds cancel. That's nice. Okay, for phi, there's no phi there, so this becomes just a constant. Phi goes from 0 to 2 pi, so I'll bring out the 2 pi. And then I'm left with an integral over theta from 0 to pi of sine theta d theta. All right, I'm going to come up top, give myself some room. So I just need to compute that integral. So we've got Q is equal to 2ab epsilon pi v0 over b minus a. And the integral of that is negative cosine theta. And we're going from 0 to pi. So when I do that, I pick up a factor of 2. Because minus cosine of pi is 1. And then minus and negative 1 gives me 2. So this becomes 4 ab epsilon pi v0 over b minus a. Yep, that's Q. So now when I compute the capacitance, Q over V, right? And we're saying we had V0 volts, so that drops out as it should. And my capacitance is that. Okay, so that gives you a second option. You can solve Laplace's equation if you like. All right, well, that's about everything that we need to say about electrostatics. And I guess we'll start to shift focus now towards magnetostatics. I will see you then.